To understand the power of Fourier transform diagonalization of operators, let's go back to this example of a horrible but typical matrix function. So in many contexts, some of them in physics very naturally, but also in engineering, when you evaluate various multidimensional Gaussians, you end up looking at a matrix which can be written as a function, but a rational function of translation operators, because Laplacian is a particular translation operator. Now, there could be higher derivatives when you study oscillations of thin plates. You find fourth order derivatives naturally. So it depends on your problem. There could be more derivatives. This is the simplest case. And I use it to show that in this case, I can use geometric series. I can make it convergent for sufficiently large M. And I showed you that this geometric series is horrifying because it has infinitely many terms. And all of the terms after you reach the order here, which is size of the matrix, all of the terms are connected, and this is some complicated mess. So what does Fourier method do for us? It diagonalizes propagator. Fourier method takes a propagator. So far in complex analysis, we were just working in two-dimensional plane of imaginary plus real. But Fourier analysis actually now works because of this wonderful property. It doesn't matter where we translate first here or that, where in hypercubic lattices, the translations commute. This Fourier analysis enables us to do d-dimensional arbitrary problems. And a typical problem has the matrix like this one, called propagator. And now we would like to compute this matrix. And the prescription is that we are supposed to sandwich it between eigenfunctions and Hermitian transpose, complex conjugate transpose of eigenfunctions. And that procedure, if M commutes with translations, should give us a result. And indeed, it turns out computing an inverse, which used to be such a horrible mess, there's nothing to it because you're just computing it on a diagonal line. So there's a Kronecker delta saying, I have non-zero entry only on diagonal, but these two guys are the same. And then there's just a function which replaces in every dimension, so it doesn't matter how many dimensions I have, those translation operators. So these are matrices of the full size on the system, but they just get replaced by their eigenvalues, and because left and right are equally good, I add them up, and I always end up with cosine 2 pi over n. That's a prime root of unity, but now its component, kth Fourier component in dimension 1, 2 to the dimensions, minus number 1. So nothing could be simpler. So it's one number each one-dimensional subspace. So while original problem was in d spatial dimensions, the Fourier transform problem is characterized by what's called a wave number, set of integers, which basically will be interpreted when you get into continuum, how many wiggles I have over the interval that I'm working on. And that's the glory of Fourier transforms. Now, in all your quantum mechanics courses, If you have taken condensed matter physics, you would see these cosines every place, because in condensed matter physics, we actually live on lattice which has a spacing, which I've here absorbed in the definition of this mass. But we actually have sines and cosines of the lattice, and they have names like Brillouin zones and God knows what. So in condensed matter, you see them all the time. In quantum mechanics and particle physics, we take line to be infinite and have infinitesimally spaced points. Then what happens is this cosine, cosine starts with 1 plus the square of this number here plus higher powers. 1 gets cancelled. The square of the number, I can reabsorb these pi's and various things in there. So I'll find that in a continuum limit, the propagator will be m squared minus wave number properly rescaled, so it's called momentum square, and that'll be a typical calculation we do in particle physics, electromagnetism, all kinds of places like that.